Here is an example about an engine block. We are trying to support this engine block here. The engine, which is not moving, has a mass of 225 kilograms. Question for you, which you don't have to answer this, but do you think that the center ring is accelerating, this center ring here? Probably not. I'm going to guess that this center ring there is not accelerating at all. That is an interesting clue to help us to determine how we can view this kind of problem. Because we can move on to this. Eventually, I'll show you this. We're going to have to find the tension in each chain. I say rope, but I mean chain here, I suppose, with this diagram. We'll need to find each tension. There are, many people would automatically look to the engine and try to find the tensions just from the engine. But there's only one thing that's touching the engine, T1. You're not going to be able to find T2 or T3 if you just draw a free body diagram for the engine, because you don't have any effect from T2 and T3 that the engine can sense. The engine only knows about the forces acting directly on it, and so it only knows about T1. If we are going to find the tension in each chain, in this case, then we need to look at something that is touching all of the chains, and that is the center ring right there. That touches all the chains. It is not accelerating, and those two pieces of information together can help us solve to find the tension in each rope. To do that, we can examine this set of equations here and look for things that will cancel, things that will end up equaling 0. These equations are all derived from F net equals MA, or F net x is equal to MAX, F net y is equal to MAY. We said in the previous question, is the center ring accelerating? No. Thus, if you have net force is equal to MA, if A is 0, then you get a whole bunch of forces equaling 0. Whole bunch of forces equaling 0. I want you to take a moment and look at all these equations and determine which one you think will be the set of equations that will correctly cancel with each other, that will add to get 0 in this example. The correct answer for this is B. B, as in Bravo, T1y plus T3y should equal 0, and T2x plus T3x should equal 0. This means that the y component of T1, I'll look at T1. Well, T1 is just completely vertical, so all of T1 is just going to be T1y. T1y plus, and that's pulling on the ring down. You can see that according to the ring, to this ring in the center, T1 should be pulling down. So T1 will represent a downward force. The downward force from T1 should cancel out with the upward force from T3. T3 is going to have some up and some to the side. So it'll have some y and some x to it. So the downward force from T1 should equal the upward force from T3. And likewise, T2, well, T2 is pulling to the left, and T3 is pulling diagonally, but it's pulling somewhat to the right and somewhat up. And so the leftward amount of T2, which T2 is all just to the left, that should cancel out with T3. This right here gives us effectively all the information we need to solve for the tension in each rope. We have our engine block. I've actually redrawn it, focusing on just that center ring right there. I've got T1, T2, and T3 pulling on that center ring, and I recreate what the answer B was, but I did make one change for you to be able to see exactly what we're doing. I specified that T1y is pulling down and T2x is pulling to the left. I added in those negative signs just to be abundantly clear which direction things were pulling in. Always try to understand that, that way of looking at a problem. Thinking about taking whatever is positive and whatever is going up or to the right and leaving it positive or making it positive, and anything going down or to the left, making it negative like that. If you have something going up and something going down, you add them together, it should be less than the thing that's going up. You should subtract off. We need to find the value of each tension, T1, T2, and T3. We can do that by just starting working on these equations. Let's look at the y ones first, because I wrote those down first. If I take this and I do a little bit of algebra, I get this. This should also be pretty clear that the amount that I'm pulling up and the amount that I'm pulling down with T3 and T1, they should cancel each other out. This ring is not accelerating up, it's not accelerating down to the left or to the right. That ring is just sitting there. So the net force on that ring has to be 0. Therefore, the force in y, the net force in y has to be 0. The net force in x has to be 0. And for that to be the case, the upward amount of T3 has to be equal to the downward amount of T1 so that they cancel each other out. So that's what we're saying here. Is A equal to 0 because it isn't moving? Yes, more specifically, the net force is equal to 0 because A is equal to 0 because it's not accelerating. Now, if it was accelerating, it would also eventually start moving, and we know that a ring like that just supporting an engine block, well, that shouldn't start accelerating if it's just sitting there. So we can say that the net force on that has to be 0. We have T1y is equal to T3y. What can we do with that? Well, we can say that T1, because T1 is all in the y direction, then I can even remove that y there and just say, well, it's all T1, and that is equal to T3y, which is T3 sine theta. You can look at this problem and you can kind of draw in another angle there. That also has to be 60 degrees. If this angle here is 60, then that angle there is 60 based on some trig identity or something like that that I don't even remember, some geometry thing that I can't recall because I last did that in middle school. Anyway, I remember that that is true. You've got a parallel line, and these both have to be 60 degrees. So T1 is equal to T3 sine 60 because it's a vector. We can break it up like that. And T1 should be the same as the mass of the engine block times the acceleration due to gravity that that engine block would have to overcome to just hang there at the end of the support. The engine block is experiencing a force of gravity of mg, and T1 has to be supporting that engine block, and so it has to have a tension of mg. That's why T1 is equal to mg. That's still equal to T3 sine 60. There's not a lot more that we need to do with that because we know m, we know g, and sine 60 is just a number that we can ask our calculator. And so it turns out that T3 is 2546 newtons. You can say 2550 newtons to round to 3 sig figs. We can also, just for completeness, remember that T1, as we said, has to be equal to mg because it's supporting an engine block with a gravitational force on it equal to mg, and then say, well, that's just going to be 255 times 9.8, 2205. Just remember to write down T1 is equal to 2205. We can move on to using our x equations now. And we only have the 1 here. But doing the same kind of algebra, we see that t2x, it has to equal t3x. T2 is going completely in the x direction, so we don't need to have that x identifier on it because it's just going in that direction. And that is equal to t3x. Well, t3 goes somewhat in x and somewhat in y, so we define the component to be t3 cosine 60. And again, we have the same kind of thing. We remember from before, from y, that t3 was 2546. We plug that in there for t3. And then we've got cosine 60, which is just a number, so we can ask our calculator about that. Multiply by 2546, and we get that T2 is 1273 newtons. So you see, each of these supports, the ropes or strings or chains, I guess, whatever they are, they each have to be pulling outward a little bit. T1 is pulling on this ring down because it needs to in order to support the engine that it's supporting. This is effectively T1 is all just the weight of the engine transmitted through the chain. You can think of it that way, that the weight of the engine is transmitted through the chain to the loop there, the circle there. And then if this was more convenient, you'd just have another chain going right up to the ceiling and you wouldn't have to deal with different directions. But for whatever reason, we've got different directions that we need to deal with. If this one is pulling this way at all, then you're going to have something pulling this way. If you just cut that chain right there, then this would no longer stay right there. It would swing down somewhere. But with that chain, it will keep itself from swinging down like that. I've got a video that I want you to watch that I've posted on my YouTube that is about a ball just sitting on a ramp. And it's supported by a string. And I believe that this will also help you understand more about the forces and how to deal with them.